Hello everyone. In this class, we are going to discuss transmission lines, transmission line parameters, and transmission line equation. These topics are included in Unit 3 of the paper Modern Optics and Electromagnetic Theory in our syllabus. Now, before going into the discussion of transmission lines, we can have an introduction about the guided and unguided transmission. We know that in the satellite or radio communication, the signal is radiated into free space, which is picked up by the receivers. But in electric power transmission, the generated electricity from the source is sent to the destination or load with the help of transmission lines. This means that signals can be sent as guided or unguided. So the radio communication comes under the domain of unguided transmission. So radio communication is an example for unguided transmission. While in guided transmission, we use transmission lines or waveguides for power transmission. Example is electric power transmission. So in unguided media, the signal energy propagates through a wireless medium, while in guided transmission, the signal is transmitted either through a transmission line or a waveguide. Now, these transmission lines convey electromagnetic radiation. Usually, the two-wire transmission lines or coaxial cables are used. That depends upon the frequency. If the frequency is up to 300 megahertz, we use two-wire transmission lines. If it is up to 3000 megahertz, we employ coaxial cables. If the frequency is still greater than 3000 megahertz, we use waveguides. So let us discuss the transmission line parameters. So in order to discuss the transmission line parameters, we need to represent the transmission line as a network of elements like resistors, capacitors, inductors, etc. Let me draw a transmission line here. Here I am drawing a resistance. Why there is resistance? It is because these transmission lines are conductors. They are definitely having a finite conductivity. So there will be a resistance which is imagined to be distributed throughout the line. So I am considering a resistance here. There is a series resistance. And also while defining these transmission line parameters, we consider only unit length of a transmission line. Suppose that the transmission line is having a unit length. So we consider resistance per unit length here. It is the first transmission line parameter, first one. that series resistance per unit length. Capital R. So its unit will be ohm per meter. Resistance per unit length. So it is ohm per meter. So here I am drawing a resistance, capital R. So that series resistance is due to that finite conductivity of the transmission line. There will be a resistance, capital R. That is the first transmission line parameter. Series resistance per unit length. And now we know that a current carrying conductor has an associated magnetic field. Both the growth or decay of current is opposed, and hence it possesses an inductance. So I'm drawing an inductor here. Inductance L. So the second parameter is series inductance per unit length, capital L, whose unit is Henry per meter. And now here in this transmission line, there are two conductors which are separated by an insulating media or dielectric media in between them. So two conductors separated by a dielectric medium will give you a capacitance. So there will be a capacitance in between the two conductors, which is represented as C. So there is a shunt capacitance in between the two conductors. So the third one is shunt capacitance. Per unit length. C, whose unit is farad per meter. And now, even though there is an insulator in between the two conductors, it may not be perfect. So that there can be a leakage of current in between the two conductors. So due to that leakage of current, there is a conductance in between the two conductors. So the fourth one is the conductance. I'm representing here capital G. So the fourth one is the shunt conductance per unit length. Capital G, whose unit is mho per meter. So the shunt conductance is only due to that leakage current. So you should remember that this resistance per unit length is not equal to the reciprocal of conductance. We know that resistance is the reciprocal of conductance, but here the conductance arises only due to that leakage of current in between the two transmission lines. So the resistance is not equal to the reciprocal of shunt conductance. Okay, these are the four transmission line parameters, that is the series resistance per unit length, series inductance per unit length, shunt capacitance per unit length, and shunt conductance per unit length. Now let us try to derive that transmission line equation, otherwise known as telegraphy equation. So transmission line equation. To derive the transmission line equation, here I am drawing a transmission line. See, in the discussion of transmission line parameters, we have imagined a transmission line having unit length only. But here I am considering a transmission line having a finite length delta x. So suppose that this is a transmission line having a length delta x. So what will be the resistance here? And I have drawn these 4 transmission line parameters here. What will be the resistance of this resistor? It is definitely R into delta x. Why we multiply delta x there? Capital R is the resistance per unit length of the transmission line. So while considering the length delta x, the resistance will be R into delta x. So similarly, the inductance is L into delta x, and the capacitance is C into delta x, conductance is G into delta x. Now, suppose that the voltage given at the input side is V, and at the output side it is V plus delta V, and the current at the input side is I, and the current available at this side is I plus delta I. So now let us try to write the difference in voltage, that is the expression for delta V. How can we write delta V? Delta V is equal to, according to Ohm's law, the potential difference is equal to current into resistance. Here, the potential drop is due to the presence of that series resistance and series inductance. So, while considering that difference in voltage, it is equal to current into resistance. Resistance means the impedance offered by that series LR circuit. So we can write it as the resistance of the resistor plus inductive reactance of the inductor. What is the inductive reactance of the inductor? J into L omega into delta x, where omega is the angular frequency of the signal, into I. I am giving and I am giving a negative sign here. Why should I put a negative sign there? It is because the voltage available at this side, or the voltage available at the input side, may not be same as the voltage available at the output side. According to conservation of energy, either the two voltages will be the same, otherwise the voltage at the output side will be less than the voltage available at this side. In order to represent that decrease in voltage, we have given a negative sign here. So let us write delta V is equal to minus of R plus J omega L into delta X into I, or delta V by delta X is equal to minus of R plus J omega L into I. Now suppose that this delta x is infinitesimally small, so limit delta x tends to 0, delta V by delta x is equal to minus of R plus J omega L into I, or dV by dx. Limit delta x tends to 0, delta V by delta x can be written as dV by dx is equal to minus of R plus J omega L into I. This is equation number 1. And if we differentiate this equation once again, we can write d squared V by dx squared is equal to minus of R plus J omega L into di by dx, equation number 2. So in the similar fashion, we can write the expression for the difference in current delta I. So the difference in current occurs due to the leakage of current in these two arms. So there can be a small current flowing through this arm and also through this arm. There is an insulator in between the two conductors, but it may not be perfect, so that there can be a leakage of current through these two arms. So we can write the current as, by Ohm's law, current is voltage by resistance. That by resistance, that is 1 by resistance, can be written as conductance. So that the first one I am considering is G into delta X plus J omega C into delta X into V. Here also I am giving a negative sign to show that decrease in current. So delta I is equal to minus G plus J omega C into delta X into V. So delta I by delta X is equal to minus of G plus J omega C into V. Here also imagine that delta X is infinitesimally small, so that limit delta X tends to 0, delta I by delta X is equal to minus of G plus J omega C into V. That is, di by dx is equal to minus of G plus J omega C into V. This is equation number 3. Let us differentiate this equation once again. So d squared I by dx squared is equal to minus of G plus J omega C into dV by dx. This is equation number 4. So let me take the next board. So here we can write those 4 equations, that is equation number 1 to 4 for further discussions. So the first one was dV by dx is equal to minus of R plus J omega L into I. This was equation number 1. And equation number 2 was d squared V by dx squared is equal to minus of R plus J omega L into di by dx. This was equation number 2. And equation number 3 was di by dx is equal to minus of G plus J omega C into V. This is equation number 3. Now d squared I by dx squared is equal to minus of G plus J omega C into dV by dx. This is equation number 4. Now see in equation number 2, there is di by dx. This di by dx can be replaced by this minus of G plus omega C into V. So in equation number 2, I am substituting equation number 3. That is, di by dx is going to be replaced by minus of G plus J omega C into V. So equation number 2 is modified. That is, d squared V by dx squared is equal to minus of R plus J omega L, and that di by dx is replaced by minus of G plus J omega C into V. So d squared V by dx squared is equal to R into R plus j omega L into G plus j omega C into V. This value, that is R plus j omega L into G plus j omega C, is replaced by another constant gamma squared, that is d squared V by dx squared is equal to gamma squared into V. This gamma is known as propagation constant. This is equation number 5. This propagation constant can be written as alpha plus j beta, where alpha is known as the attenuation constant. And beta is known as the phase shift constant. And that expression for gamma can be written as gamma squared is R plus j omega L into G plus j omega C. So gamma is root of R plus j omega L into G plus j omega C. So in the similar fashion, we can write the expression for d squared I by dx squared. So similarly, we can write the equation for d squared I by dx squared. So d squared I by dx squared can be written as gamma squared into I, equation number 6. These two equations, that is equation numbers 5 and 6, are known as the telegraphy equations or the transmission line equations. Okay, so we have derived the transmission line equations. D squared V by dx squared is equal to gamma squared into V, and d squared I by dx squared is equal to gamma squared into I. Where gamma is a constant known as propagation constant, which can be written as alpha plus j beta, where alpha is the attenuation constant and beta is the phase shift constant. Now we can write the solution for these two equations in the next code. So the two equations are d squared V by dx squared is equal to gamma squared into V, and d squared I by dx squared is equal to gamma squared into I. Now the solution of this equation can be written as V of x is equal to V plus V minus. So the solution contains two voltages, that is V plus and V minus. And this V plus represents that transmitted voltage through the transmission line, and that V minus represents the reflected voltage, that is the voltage reflected from the end of the transmission line. So it is having two parts. The first one is the transmitted voltage, and the second one is the reflected voltage. So this V plus can be replaced by V of x is equal to, that V plus can be replaced by V0 plus e raised to minus gamma x. So this one represents, that is V0 plus e raised to minus gamma x, represents the transmitted voltage. Gamma is a propagation constant, and that negative sign here represents a wave traveling in the positive x direction, which means that transmitted voltage is represented by this term, that is V0 plus into e raised to minus gamma x. V0 plus represents the peak value of voltage. So plus that V minus can be replaced by V0 minus e raised to gamma x. And this term represents, that is V0 minus e raised to gamma x, represents the voltage traveling in the negative x direction, that is the reflected voltage. So In the similar fashion, we can write the expression for current, that is Ix is equal to I0, I plus plus I minus. That I plus can be replaced by I0 plus e raised to minus gamma x plus I0 minus e raised to plus gamma x. So these two are the solutions, that is Vx equal to V0 plus e raised to minus gamma x plus V0 minus e raised to plus gamma x, and Ix is equal to I0 plus e raised to minus gamma x plus I0 minus into e raised to plus gamma x. So these two equations are the solutions of the telegraphy equations. Now suppose that our transmission line is of infinite length, that is infinitely long transmission line. If we suppose that our transmission line is of infinitely long, so we can write Vx is equal to V0 plus e raised to minus gamma x only, because if the transmission line is infinitely long, there will not be any reflected voltage, because the transmission line is endless, so there cannot be any reflection. So if the transmission line is of infinitely long, Vx can be written as V0 plus into e raised to minus gamma x. There is no reflection. Similarly, the current can be written as Ix is equal to I0 plus e raised to minus gamma x. Now, if we take the ratio of voltage to the current at any point in an infinitely long transmission line, that is V0 ratio of V0 plus to I0 plus, that is known as characteristic impedance. So we define characteristic impedance only for an infinitely long transmission line where there is no reflection. So characteristic impedance is the ratio of voltage and current at any point on an infinitely long transmission line, which can also be written as minus of that reflected voltage, that is V0 minus divided by I0 minus. That is the negative of the reflected voltage to the reflected current. So it can be shown that the characteristic impedance, the expression for characteristic impedance Z0 is equal to root of R plus J omega L divided by G plus J omega C O. This can also be written as R0 plus Jx0. It can be represented like this also. So this is the expression for characteristic impedance, which can be represented like this. And the reciprocal of that characteristic impedance is known as characteristic admittance. So characteristic admittance I0 can be written as 1 by Z0. The reciprocal of characteristic impedance is the characteristic admittance. So we have seen that propagation constant, characteristic impedance, etc. are the characteristic properties of a transmission line. They are independent of the length of the transmission line. So the length of the transmission line does not appear in the expression for characteristic impedance or characteristic admittance or the propagation constant. So these quantities are all independent of the length of the wire. They depend only on the transmission line parameters such as resistance, inductance, conductance, capacitance, and also on the frequency of the signal, that is angular frequency of the signal, omega. Okay, that's all about today's class. In the next class, we will discuss some special cases. Thank you.